So, greetings everyone. We'll start our lecture, we'll continue our lectures on programming languages, and today we will look at semantics, or the meaning of what the programming language does. And so we've seen syntax, which defines how we write things, basically, right, how we parse. Previous lecture we saw how we parse the syntax. And today we'll look at the semantics, and this is a topic, it's a huge topic, because there are many different ways of defining the meaning of a programming language, it turns out. And so the answer, how do you do it? It depends what you want. For what purpose you are doing this definition. Are you actually implementing a new version of your language? Are you trying to learn a language? Are you trying to make sure the language does the correct thing, like proofing the language? Different things. So I recall this quote by the Ludwig Wittgenstein, limits of my language mean the limits of my world. So how we use a language sort of limits what we do, basically, right? Sort of like you can get into this philosophical discussion, right? What a meaning of word is. So that's what we're dealing today. What does equal sign mean, right? What does 2 + 2 mean, basically, right? So again, it's sort of like, seems like, yeah, why complicate things, right? And computer scientists are just like philosophers, they like to complicate things. So we look at various ways we can complicate our life. Again, and it's not just for nothing. Again, as far as practicality, we'll see there's some more practical things we can do than others. So this is actually comes from this diagrams comes from regular languages, meaning normal human languages, right? You have phonetics, phonology, morphology, right? Tokens, and we got syntax, we got semantics, right? Which is today's topic, right? And then also we'll have pragmatics, which is not really. We won't really cover separately in this course, but it is also sort of like how we sort of like the good style or the good, I don't know, I won't call it good vibe, but a good way of, the correct way of using some particular language. And again, it applies to or human languages, right? And also we call it idiomatic usage of language, idiomatic English, for example, right? And also goes to the programming languages. So there's three things. So syntax is a set of rules. Again, by now you know what. So if statement in C language, right? That's a syntax, right? Semantics, what does it do, right? So here, of course, it's not a full if condition, but of course, we can read here. Okay, yeah, code to execute if condition is true. So by now, of course, it's all sort of in our minds what it does, right? But how do you define this so sort of more formally, right? So we can say, okay, this is, we can write it like sort of semi-formally, right? And this is semi-formal definition, right? If statement, if code block will run only if its parentheses evaluated true, right? So syntax doesn't tell you, right? Theoretically, this could be a for loop, right? I mean, you can make people have done evil things with macro preprocessors in languages, right? You can rename things, right? And if loop, like if you look at this here, right? Evil C++ defines, right? Macro evil. Well, let's look at some. Right. Let's see if we can look at some examples. Maybe no. This like I want something is funny. Things to commit before you leave your job. Yeah, that looks like good, right? So structure union, define if while. Right, define else, right, define break, right, define if, so define double float, right, so that's also evil, right, so what is this, so some things are really evil, right, you define double as a float, it means you'll have less precision, right, we usually don't use floats, right, so again, since this is a preprocessor, right, it will keep copy replacing things, right, before the compilation step, right, if while, that's kind of evil too, right. Right, each time you write if, you have a loop. Because the thing is, some of them are kind of easy to spot, right? You have a forever loop, you'll figure out something is completely wrong, right? You have a loop inside the if instead of if, right? But volatile and double, these are kind of evil, right? And structure union also is, who knows, who remembers of C++, this part here, what's happening here, right? Define structure as a union. Do you remember how the union does? Yeah, combine something. Well, structure, remember that structures, you have a couple things, right? But union, what it does, you only have one field, basically. Basically, you get the use union for different data types, but you access same data basically. You can access it as a integer, as a float, as a what else? A char, right? Array, right? But it's the same data underneath. So this becomes truly evil if somebody is using structure. They think, okay, we have separate boxes for all my data, right? Underneath, actually, it's a union on your, your two integers actually are sharing the same data space, right? But I would imagine it would probably break on most compiles for some complicated structures, right? But still, quite evil, right? Quite evil, right? These are easy. Which ones? Oh, yeah, define my pi. Yeah, yeah, 3.2. Define floor as ceiling. That's also evil, right? Right. Random. This is also kind of evil. Define true, right? Like define true as randomness, basically. So it's almost always true. That's really evil, right? So it will work like 14 times out of 15, right? I believe, if I'm correct, if not correct, right? Random, right? So one of these, are kind of fun, right? So almost always work, right? These are also evil. Define the safe to unsafe memory handling, and so on and so on. Okay, but yeah, this is for a lecture on how to do evil things with your coworkers' code, right? But or for but yeah, but the whole point is that why I'm showing it here, because of course the if, that's actually we kind of sort of like almost all languages use if as if, right? As an if statement, right? But there's no book that says, okay, philosophically speaking, that doesn't mean it has to have the same meaning, right? Maybe in 500 years, I'll decide if is actually a loop, right? I don't know. The language changes, like human language changes, right? All new slang, some words acquire new meanings, right? And some, lose their meaning, right? So you can think of it, pretty much every 5 years. I mean, every year actually, you have new words or new meanings assigned to words, right? So, okay. So semantics, right, it's a meaning, right? Okay, but the last thing, which we don't really talk too much about today, but is the pragmatics, right? So this is a social part, how we use it best, right? So semantics syntax tells you what we can do, right? But pragmatics means how we actually use it, right? Like the best practices, sort of say. So let's see how this works together, right? And I'll provide pragmatics of 8. So simple example, Python, we all know Python, right? So let me make this bigger. Let me make this bigger. Come on, yeah. So there's style. So we have how we iterate over potato, right? Or variable, right? So we have our syntax rules, right? Right. We have syntax, right? We have syntax rules for strings, right? We also have semantics rules for strings, meaning what is how assignment works, right? So again, remember we could have some language where this means equality, right? For equal operator, right? So, but now we get to pragmatics, right? So this thing is how in Python we write. This would be idiomatic Python. Idiomatic Python, again, doesn't mean idiotic, but idiomatic, right? So a good thing, right? Yeah. We iterate, we have collection, right? And we have an iterator, right? So, works, right? Now, again, people who learn Python from other regular, normal language, like, like C or C languages, anything with loops, I mean, with indexing, right, will be tempted to use this approach, and it works, right? But it shows immediately this person is not really a Python native, right? They know syntax, they know semantics of Python, but this approach shows above approach shows the programmer is not used to, yeah. Most likely they use an out-of-date tutorial, or possibly, or even more likely, they were C or Java programmers beforehand, right? So that's most likely. Again, it's not a critique, right? It's not a critique. It's just basically the fact that there's a pragmatic way of doing things, right? Pragmatics, right? So yeah. So again, we know what this is how to use, but again, this approach, if you need index, right, in Python, we show and use enumerate again. So enumerate, yeah, right? And this is the idiomatic way of doing things in Python, right? So sometimes there's things you can do, right, but they're not necessarily the more correct, right? And again, we can read, of course, the Python philosophy, right? And of course, again, it's a shifting thing. Like if you follow the language for Python, things change, right? Some things appear, things which were never, like for example, there are now 5 ways of formatting strings in Python, right? And no really true one. F strings are, of course, my personal favorite, but there are other ways of doing things, right? So some of these things are actually sort of like, have kind of lost their original meaning. Now, but now we go to semantics, and I'll make this smaller. Let's make it smaller, right? So semantics we can categorize in different ways. What kind of approach are you going to take? So these are like the big picture, big categories. There's operational semantics, right? We basically say how it's going to work, basically step by step, right, on some abstract machine, right? Kind of model how it works, right? And there's actually two subcategories for this. We'll look slightly into these categories. Big step semantics, right? Kind of the big picture view. What happens when you run some part of program. On the small step semantics, which is really nitpicking, right? Very, how should I say, granular, very details-oriented way of describing what happens. And these are usually used in interpreter or compiler design when you want to understand exactly what happens with your programming language when it runs, right? So there's also something called denotional semantics. You map programs to mathematical objects such as functions, sets, domains, and again, this of course requires or presumes that you have some mathematical knowledge, right? And it's completely abstract, right? So of course, mathematicians like it. Computer scientists probably, well, somewhat, right? Those who came from mathematical background, but programmers wouldn't really enjoy this, right? But you use it for proving what programs are correct, right? Formal reasoning, right?
I have a question.
Yes.
Does also the style of how you write your program goes under the semantics?
Well, would that be more pragmatic, I think. Style would be more into pragmatics because you can have a meaning, right?
Yeah.
But the way you write, we just touched on this, right? The way you write, right? Style goes into under pragmatics, right? Yeah. So that's sort of like the next the highest level basically, right? Your style, how you do it. Okay. Right. So semantics is basically okay, what it does, right? On like again, so semantics does not prescribe you the best practices basically, right? Like so style is more in pragmatic style thing. So again, I'm very biased towards the pragmatic style, of course, right? Pragmatic side. But that's why semantic style is, of course, is very important if you're actually doing like a full-blown language, right? What we're talking about right now, right? Or proving it's actually correct, right? So that's again, there's something called axiomatic semantics by Mr. or Dr. Hoare, who is famous for something else. What did he do?
Which doctor?
Hoare. You remember what he invented? For last on algorithms. You remember?
I remember his name.
Yes, he went to Moscow. He was an Englishman. He went to Moscow study.
Oh, he thought there were one sorting calendar?
Yes, which one?
It was Quicksort?
Yes, good guess, Quicksort. And also, he's famous for the billion or $1 trillion mistake because he invented null pointer, right? So that's his fault. So we can blame everything on him. But yeah, the thing he was really proud of was this whole logic, right? The way of specifying a program by logical properties, because he was a logician actually, under like his background, right, in 50s before the programming language were really fully developed, right? He was one of the guys who actually developed like Algol, one of the big languages, like the influential languages. But he came up with this whole logic basically, and so you specify a correctness of program in terms of assertions about the states. Again, very abstract, right? But you can if you set up your programming language using this axiomatic, you can prove things about the language, right? Again, very good. Again, for certain things, right? Again, you can use algebraic semantics, right? Again, transformations, simplifications. Again, modeling abstract data types, categorical. This is something, categorical semantics, there are people who are really heavy into category theory. It's a branch of mathematics, right? So you model all your programs as mathematical structures, right? You've probably heard of these things as functors, monads, right? Very abstract. Again, good for functional programming, formal reasoning again. Now, then there's action semantics, right? So basically, you describe computations, what you do, as actually some sequence, basically, right? So this would be sort of like, I think this is getting something more, something we can use, actually, closer to what we can use, right? I hope this is still recording, right? I'm recording, yeah. All right, so something we can actually use ourselves, like in language design. Abstract interpretation, basically, right? Sort of like map a program to some abstract domain, basically, right? So, game semantics. That's a very interesting way of doing it. So showing what your programming language does. So you basically model your programming language interactions like assignment, multiplication, loops, if statements, and so on, sort of as moves in some sort of game, basically, right? Again, where would this be useful, right? You can do this for if you're modeling some interactive or concurrent behaviors. Very important in today's world. We have a lot of concurrent processes, right? Parallelism, everything's parallel, right? There's tendency, right? So this game semantics way of modeling, showing what the language does with these little mini games, right? Interactions, right? Can be good for analyzing this concurrency and communication, basically, in different processes. So another approach, right? Translations, again, this I like, right? Translation semantics basically sort of say, okay, you have a language, right? And you basically show what the equivalent is in another language, which hopefully everyone knows. Because what's the issue with these previous things? Well, they require some new knowledge, right? And require maybe learning this mathematical notation for certain domain, right? No mathematician, just like no programmer knows all the languages, right? No mathematician knows all the mathematical theory, right? There's no generalists anymore, right? Since John von Neumann, right? So this means that you have to learn something extra, which is questionable whether you actually need it, for your daily life, right? So translation semantics, I think, is very practical because you have some very simple, maybe very simple language, right, with simple rules, right? And you can sort of like, okay, you have this other language, you say, okay, it maps, translates, right, to this other language, right? Good for compiler design, right? Code generation, optimization, right? So this is a little summary. Let's look at the summary here, right? So operational semantics, step-by-step behavior, right? For interpreter design, the notional semantics, mapping programs to mathematical objects, axiomatic semantics, logical assertions, right, and so on, right? So again, most of them are sort of, like I say, not something we would use in our daily lives, unless you're, of course, designing some formal new language, right? That, of course, might come into play, right? But very few people will do that professionally. I mean, you can do it for fun, right? So let's look more deeper into this operational semantics, right? And I believe our previous lecturer for a couple of years back, he was really heavy into this. So operational semantics, there's materials on this, quite a few extra ones, right? So for some options, no, he also mentioned this, yeah. So also mentions there's different ways of doing this, right? You can do this, you can basically do an abstract syntax, basically, right? You can define some different some rules, come up with this demonstration language, basically, right, which you map to. Okay, small step semantics, right, these individual steps, the notional semantics, axiomatic semantics, we looked at these, right. So what I really like, again, is this is my favorite way, right, the real world implementations, right. And this basically means is you have a implementation, you have like a golden standard for some language. C Python for Python is like the golden standard for Python. So if you're writing your own Python interpreter, right, or maybe compiler, I don't know, right, if it does not do the same thing as your C Python, right, it's not really full Python, basically, right. There's Oracle JDK for Java, right. Again, if you're writing your own Java, assuming Oracle doesn't sue you, right. So you you have to follow this, right. So it's not technically formal. It's technically like if you were like writing academic papers, it's not be completely like, it would not be completely correct way of doing it, right? But this is actually very practical, right? You write this interpretation, like you write your own language, right? When somebody comes to you, what does this thing do? You say, okay, here's my language standard. Check it out. If it works, that's what it does, right? You know, show me the code. It check the code. Basically, it runs. You know, it does that. Okay. I'm not going to write you a big stack of documentation, right? Well, hopefully you write some documentation too. So yeah, this leads to the next thing, right? Again, it's informal, but comprehensive, good documentation is crucial, right? So again, it sort of defines expected behavior. Again, the problem is all of these is that, well, that it's really hard. You cannot show everything that the language does, right? You cannot say, you know, 10 plus 10 is 20, right? You're not going to do that, right? You obviously, because it's, you know, you just say, okay, 2 plus 2 is, you know, something plus something is addition, right? And that's it, right? You're not going to specify for everything, right? Same for loop constructions, right? You're not going to say what running something 1 to 100 does. You just say you show a loop construct, basically, right? So, yeah. So sometimes, of course, when you, for a language, right, there is actually documentation, right, which we all use and love, right? But there also might be a standard implementation, right? And there might be, maybe there is a formal way of defining what the language does, right? So, again, translational semantics, right? I want to show you so the state of data, state of data semantics, again. So you have a x plus x, we have some language, I mean, most languages, right? We know what it does. Okay, let me see here, right? So, x is equals x plus 1, right? You can define it like with the state of diagrams, basically. Initial state is, well, x is 3, right? After this is done, x is 4, basically, right? State change diagram, right? Again, so you can define all the manipulations in this format, right? So this is very concrete, right? Because it sort of also mirrors what happens in the machine, usually, right? But and you can define new transitions. But of course, here's what's the problem with this. It's if you define everything so in such minute detail, right? It becomes extremely hard to show it for a large, complex language, right? You go crazy with doing this approach, right? Probably spend, half your life, right? So now. So similarly, more visual approach could be a state machine approach, right? Yeah. So one state calls 3, right? Plus would be here in this example would be plus plus 1, right? You get 4 and minus 1, we get 3, right? So something like this. I equals I plus 1, right? Right. You can show these transitions, right? So, but of course, we cannot use finite state machines to fully model a programming language, right? Because, of course, as we know, programming language is Turing complete, right? We need some Turing machine as well, right? So, let's go to our natural semantics, right? Big step semantics, right? So, we call them natural because it's sort of like how you write them in normal world, basically, right? You have some rules, right? You have some configuration, right? And there's some big step, right? And then there is a solution, basically, right? Final state. So here's an example how you would define if then else in some language, right? Again, most languages will follow this approach, right? If condition, right? Then, right? Else, then, right? Else state, right? Final state, right? For else block, right? Basically. Again, but it seems like the critique, which I would apply at least, is that you're sort of defining something which is also like mapping is too close to what the language says, right? I would say this mapping would be useful if you have some really weird language which does not have this normal if then else, right? Because it seems like you are overwriting what you sort of saying what you did do already. So with big step semantics, another approach is of course is like the big O problem right here, right? You see these tutorials, they show the start, there's something, and then you see the O, right? And what happened? How do you get to that step, right? That's a problem oftentimes, right? So it doesn't give you exact, I should probably, there's a little F word, right? So it doesn't give you the intermediate states of what's happening underneath, right? So for like infinite loops, so something which is not terminating, right? It's kind of really not, you can't really describe using these big step semantics, right? It's sort of readable, right? So you can use this to describe relatively complex programs, right, on program language constructs, but it's missing some steps. Okay, now, right, so usually, of course, you use some other semantic models to sort of fill in the blanks, right? So, again, you want to do the formal reasoning. So that leads us to small step semantics, right? Or we call them structural operational semantics, right? So, very small steps, right? So incremental state. You have so basically everything that happens on your computer, right, by this programming language constructs will be strictly defined. S1, S2, S3, and so on and on, right? You basically capture everything, right? So usually there's this rule, right? If something, then, basically if S equals that, right, then there is a transformation. So let's look at this example. Maybe not this one, maybe you can see this also in materials here somewhere, here we have it. Yeah, something like this, right? You can say this here, right? Natural semantics, right? Yeah, yeah. And you can basically draw this, what's happening underneath, basically. But let me see if we can show here. This is not, I don't have very good, latex not really running for. Kind of bad syntax. You can't really see it here very well, right? But again, these small steps basically define everything that happens, basically. So again, extremely complex, extremely tedious approach, right? A lot of boilerplate, right? Very not really readable, right? Because again, if you look at the full description of this small step semantics, is really, you're gonna bog down in your details, basically, right? So not something I would recommend, right? So again, another approach, we could use something called abstract state machine, right? So I like that one better. Maybe actually, maybe we'll do it after the break. We will focus on that approach as well, right? So big step semantics. You have this overall effect, right? What happens basically? Initial starting state, something final. What's final outcome, right? And you miss the whatever's happening inside, right? So you just have to trust that this actually happens, basically, right? But again, simpler, right? Small step is extremely verbose, right? How does actual things happen in machine, actually, basically, right? So by that definition, you can transfer these small step semantics to this abstract state machine, basically a machine, basically, right? That kind of modeling machine which shows what's happening in your program, basically, right? Sort of like again, basically you assume, okay, there is some sort of computer running this program, right? You can sort of like, okay, this is going to be like our abstract machine which will run it, right? Good for concurrency, right? So weaknesses, right? So this ignores intermediate states. So here's an example. Add 3 plus 5 returns result 8, right? Simple, right? But the small step, it says evaluate what 3 is, what the meaning of 3 is, right? Evaluate 5, what the 5 is, right? And then you get 8 afterwards, right? So that small step on the abstract machine would be, okay, you have 2 states. You have states 3 and 5 numbers. You have an apply addition rule, right? And you transition with the state with 8, right? So all these approaches again could be used to define a language, strict definitions of a programming language, right? So static analysis, dynamic analysis, formal language specification. So this would be a formal language specification. Let's see. Yeah, a couple of minutes. Let's see what C++ language specification looks like. C++ language specification, right? I had this book at 1500 pages, right? The standard, right? What do they write? It's documentation, technically. Are they gonna mention? I think you have to pay for this, actually, if I remember correctly. I can purchase. How much does it cost? Accept all my cookies. Only 220 Swiss francs. That's like 200 euros, right?
You can likely get it for free.
Yes, of course. Yes, yes. But yeah, oh, look at these pages, 2,100 pages, right? So aren't you happy or grateful that I didn't make you read this last semester, right? 2,100 pages, right? But again, the thing is, nobody has actually, knows all the pages, right? So, but let's see. You can see some again. So it mentions C++. It's not authoritative, but again, that's an official. You can purchase. I wonder if you could. Yeah. Yeah, you see, why are C++ working materials freely available on GitHub when a standard must be purchased from me? Okay, there's copyright, right? But incremental, so technically we can get everything from GitHub, right? So it's kind of like, again, one of those things with academic publishing. Most professors will have some sort of online presence where you can get everything for free, right? But then officially, you're supposed to buy the books from or buy the papers, right? If your school does not have the subscription, right, for some material, you have to actually pay a lot of money. But usually, if you're a poor, starving student, you don't have to do this, right? You have to find just a publisher whoever made this, right, and you can find it. So that's the story here, right? Technically, some organization will have to pay these 200 francs, right? I don't know how many they sell, probably a couple copies a year, I don't know. But officially, you can get here, right? So here is the latest version. If you know how to compile LaTeX, right? So who here use LaTeX? Use LaTeX.
Well, I've used it once and
Yeah.
that's it.
Yes. So if you ever get into this publishing in general, right? It's a standard, and we can blame who. Do you know who you blame it for? Who is the inventor of LaTeX? Well, Tex actually. It is Donald Nuss, right? Or computer scientist. It was basically his procrastination project in 1970s. He was writing a book on algorithms, and instead of doing that, he said, "Okay, I'll write a new typesetting system for desktop publishing, basically, right?" And now, basically, it's a standard, right? It makes really nice documents. Okay, let's see. So I had to install it. Debian, Fedora, Arch, my on Windows. I had to install Perl. No, I don't want to install Perl on this computer, right? And then I have to make, right? And I can make a actually documentation, right? So it's kind of funny, yeah. Maybe you can. So basically, yeah. So technically, you can get all the papers. But yeah, let's see what I have. Anything? A couple more minutes before the break, or maybe we can take a break now. Yeah, let's take a break till 12:55. Okay. So then we'll find the papers.